Okay, we are ready to start our lectures on Chapter 6, which will cover Laplace transforms. And today's lecture will cover the material in section 6.1 and 6.2. They fit together nicely and there's not too much material, so it's reasonable to do it in one lecture, I think. Okay, so the first thing we want to talk about is an integral transform. So an integral transform means you start with a function which we'll call little f. You multiply it by some other function which we'll call the kernel of the transform. So that's a function of two variables, t and s. You integrate with respect to, this is a typo, you integrate with respect to t. That will give you a function of s, which we'll call capital F of s. And so this kernel gives you an integral transform, which takes you from the function little f, which is a function of t, to the function capital F of this transform variable s. Okay. Now, there are lots of kinds of transforms, and they come up all over in physics and in chemistry and in engineering, and there are just millions of them. The one we're going to focus on in this course is the Laplace transform. So that's a particular kind of transform for a particular choice of the kernel. Before I do that, let me say that when you do these integral transforms, almost all the time, one or both of these intervals, endpoints of the intervals are infinite. So you're ended up with having to deal with integrals over infinite intervals. And so that means you have to worry about convergence or divergence. Those things can become infinite themselves. They don't necessarily have finite values. So it gets a little tricky and you got to be careful. Okay, so you can have finite intervals, and then for the Laplace transform in particular, we'll have the interval from 0 to infinity. So we want to focus on the Laplace transform. So the Laplace transform is, let's call it capital F of s. You're given a function little f of t. The Laplace transform of that function little f is you multiply by e to the minus st. You integrate from 0 to infinity with respect to t. That gives you a function of s, and often we denote the Laplace transform. We'll use those notions interchangeably. We'll sometimes write script L, Laplace, of f as a function of s to remind us that we're taking the Laplace transform of this given function f. Sometimes it's more convenient to just always remember by the Laplace transform, we'll use the capital letter. So the Laplace transform is a particular case of this integral transform where here's the kernel. It's the exponential function. Okay, so what we're going to see the Laplace transform do in a few sections is the Laplace transform will take an ordinary differential equation. Will Laplace transform everything in the equation. You know, the old rule from elementary school that whatever you do to one side of the equation, you do to the other. Same thing with the Laplace transform. If you Laplace transform one side, you Laplace transform the other. We'll get some properties of the Laplace transform, and then we'll see that this transformed equation is actually an algebraic equation to solve. So we can solve and get capital S, F of S, just by solving an algebra equation. And then we have to figure out how to invert back to get from capital F back to our function little f, the one we were really interested in. Okay, so there'll be a several step process, but in doing so, we'll be allowed to evaluate differential equations with discontinuous, inhomogeneous terms, things we were never able to do before. Okay, so because these transforms go over, the Laplace transform is over an interval which is infinite in length, we may have functions that don't have a Laplace transform in the sense that the integral becomes infinite, okay, or the integral diverges. So what conditions on the function little f would ensure us that little f has a Laplace transform? So this theorem tells us at least one set of conditions. So suppose that the function little f is at least piecewise continuous on every interval 0 to t for every possible t. So that means basically piecewise continuous on the half line. And suppose that you have, these should all be positive constants. Usually they call this A. I don't know why I called it alpha in these notes. Let me call it A. So suppose that there exist constants K, M, and A, all three greater than 0, such that the absolute value of f of t is less than k e to the at for all t big enough. Then the Laplace transform of little f exists for s greater than a. Okay. Now, in general, I'm not going to show you many proofs, but in this section on Laplace transforms, we'll do some because they're just basically calculations and it makes things make sense. Okay, so we want to show that the Laplace transform of the function f under these conditions on little f exists. So we look at what's the definition of the Laplace transform? That's this one, okay? So now I can break this integral over the interval from 0 to infinity into two separate integrals. One where we go from 0 to m and one where we go from m to infinity, okay? Now on the interval from 0 to m, f of t is piecewise continuous, so it's bounded. Therefore, it's integrable. The exponential is everything nice. It's continuous, it's integral, all those good things. So this is integrable, and this is definitely finite. So it's bounded or finite. So that can't give us any trouble. Remember, the Laplace transform is not going to exist when this integral becomes infinite, okay, or diverges. But since this integrand is integrable, the first piece cannot cause you any trouble. So let's look at what happens on the second piece. So what I do is I go to this equality, I put some absolute value signs around it. That makes it a less than or equal to. And the absolute value of the sum is less than or equal to the sum of the absolute values. And the absolute value of the first one, that's bounded. And now in this one, you can take the absolute value inside the integral. And again, it makes it bigger, but that's okay. We have a less than or equal to here. The exponential is always positive. I put the absolute value signs around this guy and I integrate with respect to t. So we have what? We have our first term, which is bounded. Now, according to this hypothesis on little f, make sure you can see it right here, I can replace f and make this inequality even bigger by replacing f by e to the k, which I write here, times e to the at, because we're on the interval where t is between m and infinity. In other words, t is bigger than m. And then notice that this is e to the, this should be a minus s plus a. So that's e to the t minus s plus a dt. So when you integrate that, you get e to the t minus s plus a divided by minus s plus a, and that's evaluated from infinity to m. Okay, so when I say evaluated at infinity, I really mean you evaluate, you take the limit as b goes to infinity, and you evaluate this from b to m. But we've done this in class before, so we all know what we mean by that. So now, when is this finite? This is finite as long as minus s plus a is negative. Because when you have a really big number up here, if this coefficient isn't negative, it's going to be, this whole term will be infinite. So we need that coefficient with the t to be negative, which is the same thing as saying that a is less than s, which is what we claimed in the theorem. Okay, so that does it. Okay, so the Laplace transform exists if a function is exponentially bounded, the absolute value of the function is exponentially bounded when when t gets really big. Okay. All right, so let's compute a Laplace transform. suppose we want to compute, um, suppose we want to compute the Laplace transform of sine AT. Okay, so what is that? That's going to be the integral from 0 to infinity of e to the minus st times sine AT dt. Okay. All right. So how do you integrate something like this? All right, this is one of those exponentials where you're going to have to do the integration by parts. Okay, and so let's see. When we go to integrate by parts, I'm going to let let's let u be e to the minus st, and then du. I'm integrating with respect to t, so this will be minus se to the minus st dt, and then dv is going to be equal to dv is equal to sine at dt, and then v is cosine at divided by a, with a minus sign. All right, the minus sign. Okay. So by integration by parts, this is equal to u times v. So that is minus e to the minus st times cosine at over a, evaluated from infinity to 0, minus the integral from 0 to infinity of v times du. So let's see, that will be a minus, you have a minus v times du, but this is a minus and a minus, so all total we get a minus. There's a 1 over a here, and then we have se to the minus st cosine at dt. Okay. All right. So so this is equal to, all right, as t goes to infinity, this one's going to 0 because s is positive. So as long as s is positive, this will go to 0. And then you subtract the value at 0. So you get 0 if s is greater than 0. And now you subtract the value at 0, so that at 0, I will get e to the 0. Cosine at 0 is 1, so I get a 1 over a. Okay. And I'm a little concerned. I may have the sign wrong there. Let's see. Be careful. I have an e to the minus st, so then when I differentiate, I get minus se to the minus st dt. dv is sine. When I integrate, I get minus cosine. That's right. And now u times v is minus the integral of v times du. So minus, and that minus makes it a plus, it makes it a minus. Okay, now this looks okay. Maybe in my notes I had it wrong. Okay, I'm remembering it wrong. So now, again, what do we do here? You have to do the integration by parts again. So now when you do the integration by parts again, you better do u is e to the minus st, and then du is minus se to the minus st. S is not the variable of integration, so I can move it out in front. Or you could keep it here with it if you like. And then this is an s squared because it's not the variable of integration. So we're okay by doing it that way. And then dv is going to be cosine at dt. And so when you integrate cosine, you get sine at divided by a. Okay. So now this came from the first two terms. And now when I do this, I have a minus 1 over a times u times v. So that will be se to the minus st sine at divided by a. evaluated from infinity to 0 minus the integral from 0 to infinity of v times du. So that's a minus and a minus here. That'll give me a plus. I have an s squared from this one, and I have an a from this one, and then I have an e to the minus st cosine sine a t dt. Sorry. So that's not real clear, but that should be sine a t dt. All right, so let's gather all that up. That means we have a 1 over a, and then we have a minus 1 over a times. Okay, now what is this one? As t goes to infinity, if s is greater than 0, this exponential goes to 0. Sine is bounded between 1 and minus 1, so this thing goes to 0. And if you subtract the value at 0, so this is 0 if s is greater than 0, and then you subtract the value at 0, but at 0, sine is 0. Okay. And then I have a plus s squared over a squared times the integral from, s squared over a, right here. The integral from 0 to infinity, e to the minus st sine a t dt. But notice, this thing is exactly the Laplace transform of sine at. So bring this to the other side. So we will have a 1. Now be careful, you have a distributive property here. So this is a minus s squared over a squared. Maybe I should write out one more time. I have a 1 over a minus s squared over a squared times the Laplace transform of sine at. Okay. And that's equal to the Laplace transform of sine at. So you bring this to the other side. Whoops. Bring this to the other side and combine it. And you will have 1 plus s squared over a squared times the Laplace transform of sine at is equal to 1 over a. So we will write this as a squared over a squared plus s squared is the Laplace transform of sine at. So the Laplace transform of sine at is multiplying by the reciprocal on both sides gives me an a over a squared plus s squared. Okay. All right, so that's the Laplace transform, and this works if s is greater than 0. So there's the Laplace transform of sine. Okay, so a is a constant. I should have said that, but it's kind of obvious from the way we were treating it. All right, so we computed the Laplace transform for a constant. You can compute the Laplace transform for a bunch of functions, not every single function in the world, but you can compute it for a lot of functions. And you'll have homework problems that give you some practice to do that. And as you see, as you just saw in that example, you're going to need all your tricks of integration. And you have to remember improper integrals. So if you are a little bit rusty on that, get out your calculus book and review the properties of improper integrals. That is when one of the limits is infinite. Okay. All right. Another thing we're going to want to do is let's compute an easier Laplace transform. I kind of started with a hard one. So suppose we let's start with a really easy one. Maybe I should have done this first and not discourage, that might have scared you a bit. Okay, so let's do the Laplace transform of 1. That'll be calmer. So we have the integral from 0 to infinity of 1 times e to the minus st dt. Okay, because I multiply by 1. All right, so integrate that. If you can't integrate that, you're in real trouble. You're integrating with respect to t, so s is acting like a constant. Okay, So that's the integral from e to the minus st divided by s, evaluated from infinity to 0. And so as t goes to infinity, this goes to 0 if s is greater than 0. If s is negative, it goes to plus infinity. There's no Laplace transform, okay, because then the integral becomes infinite. And now we subtract the value at 0, and the value at 0 is e to the 0, which is 1. I'm sorry, this should be a minus s. It's e to the minus st divided by minus s. Okay. So then we have a minus s. So this becomes 1 over s. So the Laplace transform of 1 is 1 over s if s is greater than 0. Okay. All right. So is that a little better? I hope so. That one's easier. Okay. So not all the Laplace transforms are terrible. Let's do another one that's pretty easy. Let's do the Laplace transform of e to the at for a constant. So a real number. So this will be, by definition, the integral from 0 to infinity of e to the minus st e to the at dt. Okay. All right, so now when you go to integrate this, you write that as e to the t times a minus s dt. Okay. So when you integrate, you will get e to the t a minus s divided by a minus s from infinity to 0. Okay, and so this is going to be finite when? Only when the t is going to getting really, really big. So the coefficient, the constant multiplying it better be negative, or this is going to go to infinity. So this is finite only if, or this goes to 0 rather, if a minus s is negative. That is to say, s is greater than a. Okay. And then you subtract the value at 0. So at 0, you get e to the 0, you get minus a minus s. Okay. But that is 1 over s minus a, and that works if s is bigger than a. So the Laplace transform of e to the at we worked out, and it's this if s is bigger than a. Okay. Okay, we did the one that was signed, which was a really difficult one. We did that first. Okay. All right, let me do another example, but before I do it, we're going to introduce a function or a notation that we're going to use a lot. It's standard notation. Okay, so let's look at a function which has a jump in it. So suppose I look at the graph of the function. Let me call this, let's take the function which from 0 to 1 has the value 1. And then at 0, let's say it doesn't take the value, it takes any value. Let me call it k. So at t equals k, at t equals 1, it takes the value k. And then for any t greater than that, it takes the value 0. Okay. So in other words, let me call this u1 of t, because that's a classic way to do it. It takes the value 1 for t between 0 and 1. And you can make it at 0. Okay. And then you make it 0 for t greater than 1. And you can make it anything at t equals 1. It doesn't really matter what you make it at one particular point. Okay, so this is a classic step function, and this one's stepping down. Okay, so we'll call that u sub 1 of t, and we'll use that notation to mean the u sub some number will mean the function that's 1 to the left of that number, in this case 1, and it's 0 to the right of that number. Okay, so that's a graph like this. Okay, so now I ask you, what's the Laplace transform of u1 of t? Okay, so let's compute that. By definition, and by the way, on the test and on the final, you will have to do some Laplace transforms by definition. And we're going to have tables to look it up on, but if I ask you to do something by definition and do all the calculations and you just find it on some table somewhere and you write down the answer, that's not sufficient. You have to know how to do some of these calculations. Okay, so what does u1 of t do? Well, let's see, u1 is 1 when t is between 0 and 1, e to the minus st, and u1 takes the value 1 there. If you want it, the value t, k is only at t equals 1, but if you took the integral from 1 to 1, that would be 0, because the integral over any point is 0. Think of it as the area under that point, that's a line, and the area of a line is 0. Plus the integral from 1 to infinity of e to the minus st. And what's the value of u there? It's 0 dt. So this one becomes 0 because you multiply by 0. And now when you integrate this, what do you get? You have e to the minus st dt. When you integrate that, you get e to the minus st divided by s, and you evaluate from 1 to 0. And now when divided by minus s, I did the same thing again. And now when t equals 1, it is e to the minus s over minus s minus the value at 0, but when t equals 0, you get minus 1 over s. So this becomes 1 minus e to the minus s divided by s. So that's a Laplace transform of this function. Okay. And you see, it's totally independent of the value of k. Okay. So k doesn't make any difference at all in that. Okay. So by the way, if I wrote u3 of t in this notation, u3 of t means the function that is 1 if t is between 0 and 3, and it's 0 if t is strictly greater than 3. Okay, so that's what I mean by that notation. We'll stick with that notation for the rest of the year in this course. It's pretty standard. You see this in most every book. Okay. All right, now that's some basic calculations about the Laplace transform for a few easy functions. The important thing is, so Laplace transform, which I'll often abbreviate as just LT, because I love abbreviations. So the Laplace transform is important for many reasons. One big one is it takes differentiation to multiplication. Okay, and so now I'll show you what I mean by that. Okay, so we'll see some examples. Now, all right. So suppose well, let me state it as a theorem because it's really important. Okay, so suppose our function f is continuous. Its derivative is piecewise continuous on the half line from 0 to infinity. And suppose absolute value of f of t is less than or equal to k e to the a t for all t greater than or equal to m. So suppose there exists a k, an m, and an a all greater than 0, such that this is true. Then the Laplace transform of the derivative of f exists. And the Laplace transform of the derivative of f is equal to s times the Laplace transform of f minus the value of f at 0. Okay. All right. So let's see why that's true. Because that just seems way too magical to just leave it at that and just go declare that's to be the truth. So let's see. It turns out to be really easy to see why this formula holds. What's the Laplace transform of the derivative of f? Okay, so by definition, that's the integral from 0 to infinity of e to the minus st times f prime of t dt. Okay, so that's the definition of the Laplace transform of a function. And right now our function is f prime, right? So now I don't know what else to do with this. I'm going to integrate by parts. And when I do my integration by parts, I'm going to integrate the f prime, but I'm going to differentiate this guy. So I'm going to let u be e to the minus st, and then du is minus s e to the minus st dt. And I'm going to let dv be f prime of t dt. Then v is f of t. Okay, so that's my integration by part substitution. And so this is equal to u times v. So that'll be e to the minus st times f of t, evaluated from infinity to 0, minus the integral from 0 to infinity of v times du. So that will be e to the minus st f of t dt. And there's a minus s here, so this will be a plus s. S is not the variable of integration, so I can write it out in front of the integral. Okay. And now stare at this for a minute. This integral is the Laplace transform of f. So far this is equal to the Laplace transform of f prime is equal to, this piece is s times the Laplace transform of f, plus, now as t goes to infinity, what happens to this thing? Well, the f, as long as s is greater than 0, this will go, the exponential term will go to 0. And we assumed that the f, when t gets really big, is bounded by an exponential, e to the at. So this will go to 0 if s is bigger than a. So that's what we need. Minus the value at 0. But what's the value at 0? When t equals 0, it's e to the 0, that's 1, and minus f of 0. Okay, so the formula is s L of f of, well, s times Laplace transform of f minus f of 0 for s greater than a. I should have said this for s greater than a in the theorem. Sorry, left that off. Okay. Okay, so that's why that formula works. So the Laplace transform of the derivative is you just take the Laplace transform of the original function, multiply it by s, the transform value, and then subtract the value of the original function at 0. Okay. So that's interesting. For the first derivative, that's what it tells us, the relationship between the Laplace transform of f and Laplace transform of the first derivative. Turns out that if you just did the same thing n times, you would get a formula for the Laplace transform of the nth derivative. So here's the corollary. Suppose f prime up to f to the n minus first derivative are continuous, and the nth derivative of f is piecewise continuous on the interval from 0 to infinity. And suppose the absolute value of the kth derivative of f of t, the kth derivative of f of t is less than or equal to k e to the a t for all t greater than m. Suppose there exists, a k, m, and an a positive. So that this is true for each k from 0 up to n. And the Laplace transform of the nth derivative of f of t exists. And the formula for it is the Laplace transform of the nth derivative of f is s to the n times the Laplace transform of f minus s to the n minus 1 times f of 0 minus s to the n minus 2 times f prime of 0, and you keep on going until you get to s f to the n minus second derivative at 0 minus the n minus first derivative at 0. So it's similar to the formula we had before, but you don't just subtract the value of f at 0, you subtract decreasing powers of s multiplied by increasing powers of the derivatives of f, starting with the 0th derivative. Okay. So the proof of that would take induction. We're not going to do that. It's just integration by parts n times, really, and induction. And really, you need induction to prove it completely. Okay. Okay. So that's a property, that's an important property of a very important property of the Laplace transform. Here's another important property of the Laplace transform. I'll state it as a theorem. The Laplace transform is linear. That is, if f and g both have Laplace transforms, that is, they're exponentially bounded and continuous and derivatives and so on. And if f and g both, and let's say alpha and beta are real numbers, then the Laplace transform of alpha f plus beta g is alpha times the Laplace transform of f plus beta times the Laplace transform of g. Okay, so the Laplace transform of the sum is the sum of the Laplace transforms. And a product inside the Laplace transform, the product pulls outside. Okay. Okay. And that's really easy to show, because if you look at the Laplace transform of alpha f plus beta g, that's the integral from 0 to infinity of e to the minus st alpha f of t plus beta g of t dt. And now the integrals are linear. In other words, the integral of the sum is the sum of the integrals, and the integral of a constant pulls outside of an integral. So this is clearly equal to alpha times this integral plus beta times this one. Oops, g of t. Okay, so that's it. That's the alpha times the Laplace transform of f plus beta times the Laplace transform of g. You're done. Okay. All right, so let's look, even if we're not really ready to go all the way on this problem, let's look at what we would start to do with an ordinary differential equation and the Laplace transform. So suppose we are given y double prime minus y prime minus 2y equals 0 with the initial conditions that y of 0 equals 1 and y prime of 0 equals 0. Okay. All right. So one way we could solve this by the method the method of finding the eigenvalues like we did before. You would have lambda squared minus lambda minus 2 equals 0. So that would tell you lambda is minus 1 or plus 2. So your general solution would look like C1 e to the minus t plus C2 e to the 2t. And then you would solve, use the initial conditions to find two equations for the two unknowns C1 and C2 and solve. Okay, so that's method one. Okay, that's an old method. It works on a problem like this. Now let's see how to, and if you did that, I'll tell you what you would get. You can check me on this later. You would get that C1 is 2/3 and C2 is 1/3. Okay, I don't want to go through that because we've done that kind of calculation a bunch of times. You would test it on it. You know how to do that. Okay. All right, so now, now we want to use method 2, Laplace transform. On this problem, we have an option. There are other problems where the old method just isn't going to work. So, you know, it's not like you have the option to do this on every problem. All right, so let's just so it's convenient for us, let's write the Laplace transform of little y. Let's call that capital Y. Okay, so we'll use it. That's very traditional. Use a capital letter for a transformed function and a small letter for the original function. Okay, so now we're going to start with, we're going to take the Laplace transform of the whole equation. And what you do to one side of the equation, you do to the other. So I took the Laplace transform on the left. I have to take the Laplace transform on the right. But the Laplace transform is linear. That's what that theorem was on this same page up here that we proved. That means the Laplace transform of this difference is the difference of the Laplace transforms. So this is Laplace transform of y double prime minus the Laplace transform of y prime minus 2 times the Laplace transform of y, and the Laplace transform of 0 is just 0. Okay. And now find that sheet. By this corollary, you know how to write the Laplace transform of the derivatives. So the Laplace transform of y double prime is s squared times the Laplace transform of y minus s to the first power, because n is 2 in this form, the way we're using this formula, times y of 0 minus 2 times, I'm sorry, n is 2, so this would be s times y of 0, then minus s times y prime of 0. Because you get to the s power, and then the 0 with power goes with the next lowest derivative from that. Okay. And now if you take the Laplace transform of y prime, by the first theorem we proved that was s times the Laplace transform of y minus y of 0. Okay, let's move that out of the way. So that tells me so the Laplace transform of y double prime is s squared capital Y. And now y of 0, by our problem, y of 0 is 1, y prime of 0 is 0. So what? This is s squared minus s times 1 minus 0. So that is s squared y minus s. Okay. And the next one, Laplace transform of y prime, is s times capital Y minus y of 0, which is 1. Okay, now we put all that into this equation right here. Okay, so s squared y minus s, that's the Laplace transform of y double prime, minus the Laplace transform of y prime, so that will be a minus sy plus 1, minus 2 times the Laplace transform of y, so that's minus 2y, is equal to 0. So let's gather all the y terms together and factor out the y. So that'll be s squared minus s minus 2. And the other terms we'll bring to the other side is equal to s minus 1. Okay. Okay, and so this is equal to s minus 1 over s squared minus s minus 2, which is s minus 2 times s plus 1. Because this thing factors to s minus 2, s plus 1. Okay. And now if you wrote that out as two separate things, if you wrote this out and asked if this was a over s by partial fractions, what's what I would say? If you tried to write this out in terms of partial fractions, okay, and work it out. That is, to work it out, you just multiply through by the denominator. That'll give you s minus 1 is a times s plus 1 plus b times s minus 2. And solve, you will get that a is equal to 2/3 and b is equal to 1/3. So now we have that y of s is 2/3 times 1 over s minus 2 plus 1/3 times 1 over s plus 1. And now you can ask which function has 1 over s minus 2 as its Laplace transform. Well, if you look back, we found that the Laplace transform of e to the at was 1 over s minus a. And that is the Laplace transform of e, so that's e to the minus 2t. The Laplace transform of that is 1 over s minus 2 by what we did before. Whoops, I'm sorry, you can't see that. And the Laplace likewise, the Laplace which function has the Laplace transform 1 over s plus 1, e to the minus t, by the calculation we did earlier, would have 1 over s minus a minus 1, so that would be that. Okay, so that's what, so we say the inverse Laplace transform, that is, you ask the question, which function has the Laplace transform 1 over s plus 1, that's e to the minus t. And which function has the Laplace transform 1 over s minus 2, that's e to the 2t. So L inverse means the inverse Laplace transform. In other words, the function whose Laplace transform is what's inside. Okay. So what we have is that capital Y of s, and the inverse Laplace transform of capital Y of s is what? That's a function whose Laplace transform is capital Y. That's little y. Okay. So putting that together with this formula that we found right here, star, taking the inverse Laplace transform of both sides, that tells us that the inverse Laplace transform of capital Y, which is little y, is equal to 2/3 the inverse Laplace transform of 1 over s minus 2, which is e to the 2t, plus 1/3 the inverse Laplace transform of 1 over s plus 1, which is e to the minus t. And that matches what we found by the other solution, okay? Okay, now sometimes it's not, this one we had the option of doing it one of two ways. Later on, we're gonna see things where it's not so easy to do it by one of two ways. Let me say one more thing. There's a table of Laplace transforms in your book, and you'll be able to use the table for most things. Sometimes you have to figure something out that's not quite on the table. It's deceptive. You think if you have a table, that's it. You just read it and that's all, but it's not, that's not quite true. And for the next lecture, I'll make sure and have a printed copy of the Laplace transform table to show you how to work with it. But for right now, let's look at one final example for this. Okay, so what we'll do is let's look at the example where it's higher order. Okay, and so now I'm going to take initial conditions that say y of 0 is 0, y prime of 0 is 1, y double prime of 0 is 0, and y triple prime of 0 is 0. So I'll try to, by putting a lot of zeros, it won't be too terrible. Okay, so we want to solve using the Laplace transform. Okay, we can find an exact solution because it's a fourth order equation. We have 4 initial conditions. Okay, so we take the Laplace transform of the whole equation. And that's equal to the Laplace transform of 0. So the Laplace transform is linear. Okay, and we're going to say L of little y is capital Y. Is this a little, L is a function of t, capital Y is a function of s. So the fourth derivative, what is that? By the rule for derivatives for Laplace transform, that is s to the fourth times capital Y minus s cubed times little y at 0 minus s squared times y prime at 0 minus s times y double prime at 0 minus y triple prime at 0. And then I subtract the Laplace transform of y, which is minus y, and that equals 0. Okay, that should have all been on one line, but I just couldn't fit it. Okay, so the only terms that involve capital Y are here. So let's factor, keep all those on one side and bring everything else to the other side. Well, let's see, y of 0, first of all, is 0, so this goes away. Y prime of 0 is 1, so this is a minus s squared. When it goes to the other side, it'll be s squared. Y double prime of 0 is 0, and y triple prime of 0 is 0. So that's it. That's all we have. And so that tells me y of s is s squared over s to the fourth minus 1. Okay. Now, if you look in a table, you won't see anything to invert the Laplace transform of the fourth power like this. Okay, so you're going to have to do something to fit it into something you see in that chart. So first thing we notice is this should factor. Again, this is where if you have bad algebra and you don't recognize that immediately, you're in trouble. Okay, because you can't solve these problems at all. So now, how do you want to do this? Well, when you see something like this in Laplace transforms, you got to try to do it by partial fractions. So I have s squared over s squared plus 1 plus, times s squared minus 1. has to be equal to, okay, when you do a Laplace partial fractions and you have something like s squared plus 1 as a denominator, what do you have to guess as a numerator? You better guess a linear term. So it's as plus b plus cs plus d over s squared minus 1. Okay. Okay, and now when you work that out, you will get s squared. Let's do this one completely. So here I'll have as plus b times s squared minus 1 plus cs plus d times s squared plus 1. Okay, so that says s squared is equal to, here I get an as cubed plus a bs squared minus as minus b plus cs cubed plus ds squared plus cs plus d. Okay, so s squared is equal to the cubic terms. What are the coefficients? It's a plus c. That's this one and this one. And now the squared terms. What are the coefficients? It's b plus d. This one and this one. And the terms with an s. What are the coefficients? It's c minus a. Okay. And then the constant terms are b, d minus b. Okay, and now this is just a method of partial fractions, which you should already know from Calculus 2 or basic algebra, high school algebra before that. So now you equate the coefficients. The coefficient of s cubed on the left is, on the right is a plus c. On the left, it's 0. So this comes from the s cubed terms. Okay. From the s squared terms, on the left, the coefficient is 1. But on the right, the coefficient is b plus d. From the s terms, on the left, the coefficient is 0. On the right, it is c minus a. And the constant terms, on the left, it's 0. And on the right, it's d minus b. So this one says a is equal to minus c. And now if you use that here, that says c minus a is minus c equals 0. Okay, and so that you solve this any way you like. This is just the way I happen to be doing it. So that says 2c equals 0, which says c equals 0, which says a equals 0. Okay, so c and a are 0. And now these two equations for b and d. So we have b plus d equals 1 and minus b plus d equals 0. Add them. That'll give you, the b's will cancel. You get 2d equals 1, which says d is 1/2. And this equation says that minus b plus 1/2 equals 0. So b is also 1/2. Okay. All right. And so now what does that tell us? Going back here, now we have a and c are 0 and b and d are both 1/2. So y of s can be written as, so we're writing this thing as this. A, which is 0, that goes away. B is 1/2. So I get 1/2 1 over s squared plus 1 plus c, which is 0, so that one goes away. And d is 1/2, so that's 1/2 times 1 over s squared minus 1. Okay. Okay, and now if you look this up on the Laplace transform table, or basically by what we did before, you see that now, hold on, let me make one more step before this. Now I want to take the inverse Laplace transform of everything. So that's the inverse Laplace transform. The inverse Laplace transform is linear, just like the Laplace transform is. Okay. And now the inverse Laplace transform of capital Y brings me back to little y of t, because this means the function whose Laplace transform gives you capital Y. And on this one, when you look at your chart, when you do in the inverse Laplace transform, you're reading from right to left. If you look for the function s squared plus 1, you will see something of the form on your chart, a over s squared plus a squared. And that's the function whose inverse Laplace transform is sine at. So this is where a is 1. So this is sine t. And in the chart, when you look up a over s squared minus a squared, you look back and you see that that's hyperbolic sine at. So this is sinh 1 times t. Okay. And that's the solution of your fourth order problem. Okay. And now if you did try to do this one by the methods that we did in the previous section for the fourth order equation, and so you would see that this is actually quicker than that. It's much quicker than that once you get used to it. Okay, so basically that's everything that's in 6.1 and 6.2. In 6.3, we'll start to talk about more discontinuous functions, and then we'll start to look at differential equations with discontinuous forcing functions, so impulse functions.